All right, so Assalamu alaikum. Today we're going to continue our discussion with solids, and we'll focus our attention mostly on phonons.
ओके। अच्छा मरियम, ग्रुप पे मैसेज कर दो। आई कैंट फाइंड माय फ़ोन। पता नहीं मैंने कहाँ रख दिया। कोई और भी आ जाए। हैदर आता है अक्सर।
जी बिलाल, क्या कह रहे हो? सॉरी।
कह रहा था ग्रुप में मैसेज कर दो कि अगर कोई उठा हुआ है तो आ जाए। हैदर आता है अक्सर। सिर्फ 2 लोग बैठे हैं क्लास में और सर भी डिस्कनेक्ट हो गए हैं। आई डोंट नो उनको पता भी है कि नहीं।
All right. All right. So can you hear me now?
यस सर।
यस सर।
All right. Okay. So we're going to discuss phonons today, but we would like to start off with where we left off yesterday. We were discussing the diatomic chain in one dimensions, and we found out that inside the first Brillouin zone, we got two branches for the dispersion relationship. In other words, we got two bands. And these bands, so this is band number 1 and band number 2, these bands come out from solving a secular characteristic equation, and the values of omega turned out to be, so this, by the way, is my omega versus k dispersion relationship. So omega square turned out to be alpha, where alpha is the spring constant, which identifies the strength of the bond between the two kinds of atoms. Each atom has a mass either capital M or small m. Cosine of Ka, where K is the lattice spacing. And for completeness, let me draw the one-dimensional crystal structure as well. Two kinds of atoms, capital M and small m, and the unit cell spacing is A, and these atoms are bound together by effectively bonds which are modeled as springs, and each spring has a spring constant alpha. So this is where we currently stand. So if I take the plus sign in between this, I will get the top band, and if I took the minus sign, I will get the minus band. So these bands are also, they have a special name as far as the vibration degree of freedom is concerned. This band at the bottom is called the acoustic band, And the band at the top is called the optical band. Now, these names come from legacy, and I'll explain where do these names come from, but that's what I'm going to do now. But if you look at the bands, there is a special behavior at the k equals 0 point, near the k equals 0 point, and a special behavior at the boundaries of the zone. And we also find out that there is going to be a band gap between the acoustic and the optical phonons. And remember, by putting k equals 0, you can find out what these energies are going to be. Clearly, for the acoustic band, the k equals 0 gives omega equals 0. And for k equals 0 in the optical band, the of frequency is going to become 2 alpha m plus m small m under root 2. So I need to take the square root because I have a square here. So this is what the dispersion relationship looks like. So now what we're interested in is finding out why are these called the optical bands and acoustic bands. And for that, we need to expand these strings around the k equals 0 point. So when k is small, this term cosine ka can be approximated by 1 minus k square a square over 2. And so let's see what comes out here. So in the small k regime, right, that is ka is cosine ka is much smaller than 1. Let's see what happens to the acoustic branch. So I take omega square is alpha m plus small m minus alpha m plus small m minus 2 over m 1 minus 1 plus k square a square over 2. This is an approximation. So I can identify this thing as the reduced mass of the system. So my omega square is alpha over mu minus alpha 1 over mu square minus 2 k a square over 2. Right. So my mu is called the reduced mass. So this turns out to be alpha over mu minus alpha over mu 1 minus 2 mu square k a square over 2. And I can determine mu square over is over m plus m whole square. So I can just put this value in here. My omega square turns out to be alpha over mu minus alpha over mu 1 minus 2 m over m plus square k a square over 2. Just get rid of these 2's. So now if my k is really small, then this term is much smaller than 1. I can do the binomial expansion. So this thing just goes away. and I'm left with mu over m plus m k a square over 2. Of course, with an alpha mu as well. Yes, I can just get rid of this. Okay. Alpha m plus m a square over 2k. So this is my omega square, and my omega is going to look like, sorry, there's a k square as well. Sorry about that. It's a k square. This turns out to be alpha m plus m to square root a k, which shows that in this small k regime, omega is proportional to k. All right. So let me just turn on the video for a minute. Do you get this point? Do you get this calculation?
Yes, sir.
All right. So in this, what does small k really mean in terms of wavelength? So does small k mean a long wavelength or a short wavelength? Small k means a long wavelength. So sound waves are long wavelength waves. So if sound waves were to transmit through this solid, the sound would undergo a dispersion relationship that will look like the dispersion relationship over here. And here the dispersion relationship is approximately linear in K. So the sound wave travels with a linear dispersion curve inside this one-dimensional solid. And for waves like sound waves, we can also come up with a relationship between the omega and the velocity. And this is something that you learn from simple mechanics. The omega is going to be equal to the phase velocity of the sound wave into k. So this phase velocity is the speed of sound waves inside the solid. And if you look at this expression here, the speed of sound inside the solid will approximately be given by alpha 2m plus m under root into the into the lattice spacing A. So that's why the bottom branch, the lower band that has been drawn in this dispersion relationship is called the acoustic band. Okay. And what you could also do is you could also insert this value of omega square into your characteristic equation and see how these atoms are going to oscillate with time. So let me do that for a minute. That will help us get a physical sense of what the acoustic mode really means. So what I'm going to do now, I am going to take this value of omega or omega square, and I'm going to insert this into the characteristic equation that we had. So if you remember, our characteristic equation was omega square m minus 2 alpha 1 plus cosine Ka and here we have omega square small m minus 2 alpha, and then again we have alpha 1 minus cosine Ka. In fact, we have, excuse me, one plus E minus IKA here. We have one plus EIK, and then we have X naught and Y naught, which are amplitudes of oscillations, right? So these are my amplitudes of oscillations on a small m and a capital M atom. So if you were to make the replacement that Ka is much smaller than 1 here, what we could do is the following. I just take my omega square and replace it with the value that I've obtained over here. So if I were to do that, I would get alpha over 2 k square a square m plus small m capital M minus 2 alpha, alpha 1 plus 1 minus so E minus IKA can be written as 1 minus IKA, and so on, plus higher order terms. Just give me a second, please. All right, so I'm back. So what we could do now is we could just insert this value of omega square that we have derived in here and expand this as 1 plus 1 minus IKA, alpha 1 plus 1 plus IKA. And of course, there are higher order terms as well, which depend upon K square, which we are ignoring for the time being. And then what we could do is, again, I need an alpha over 2 k square a square m plus m small m minus 2 alpha, and all of this multiplied by x naught y naught equals 0. So what this means, if I ignore all the k terms, which are small anyway, then this would be, I would be left with minus 2 alpha, 2 alpha, 2 alpha, minus 2 alpha, x naught, y naught equals 0. And what this means is that x naught equals y naught. Well, this means that x naught over y naught equals 1. Now, can anyone explain what this physically means? What kind of motion does this entail? Anyone? So now I have x naught is the amplitude of oscillation of one atom, one kind of atom, and y naught is the amplitude of oscillation of the other kind of atom. And both of them are in phase. So the ratio is 1. And if I allow oscillations and the two kinds of atoms are all going to the same amplitude with the same phase, what does this mean physically? What kind of picture does it conjure in our minds?
This means that they are acting like all the atoms are of same kind at that region.
Not of the same kind, they are of different kinds. They have different masses,
Same.
but they are all oscillating in complete phase with one another. And the amplitudes of oscillation is also the same. So if I were to plot this or draw this scenario, this is what the scenario is going to look like. So atoms capital M, small m, capital M, small m, so this is m, small m. The oscillation of capital M, let's say we've called it x naught. The oscillation of small m, let's call it y naught. They are always oscillating in phase in the same direction, and both of them are oscillating with the same frequency omega square. Likewise, if at some point in time atom capital M is moving to the left, atom small m is also moving to the left. So all kinds of atoms, they are oscillating in phase, they are oscillating in tandem, they are oscillating together with one another, all of them with the same frequency, and all of them are in phase. So this is characteristic of the acoustic mode at k values close to zero. Likewise, if I were to repeat this for the optic mode, in the optic mode, I would simply need to take the positive sign over here. I'll replace this with the positive sign for the optical mode. I will get a similar result, and I'll find out that for the optical mode, if I were to look at the modified approximate characteristic equation, I will find that x naught over y naught equals -1. And I can also physically interpret this in the following fashion. The atoms are all moving with the same amplitude, but they are 180 degrees out of phase with one another. So this means that if one atom goes to the left, the other atom is going to the right. Left, right. So they're oscillating in such a way that alternate springs are expanding and compressing. So this kind of motion, and each of these oscillation is also happening with the same frequency, omega square. So in acoustic modes near the k equals 0 point, all atoms are oscillating with the same frequency, and they are oscillating in phase with one another. And in the optical mode, they are also oscillating with the same frequency, all of them with omega, but they are antiphase with one another. All right. So this would really mean that alternate springs are compressing and expanding at the same time. And why is this called an optical mode? It's called an optical mode because if these masses were ions, so we had an ionic bond, so one of the masses were positively charged, the other mass were negatively charged, then we would really have what is called an electric dipole. Now, the electric dipole, the optical mode would mean that the electric dipole is oscillating from left to right, left to right, left to right. And such an oscillating electric dipole has the ability to interact with incoming photons, electromagnetic radiation. And this frequency happens to be in with the masses of atoms that are commonly available. The frequency is normally in the infrared mode. So this oscillation interacts with infrared photons, and that is why it is called an optical or an optic mode. Okay, so this completes my discussion of optical and acoustic modes, or acoustic and optical branches in the dispersion relationship. But what relationship does this have to phonons? That's what we're going to explore in a minute. But remember that for the time being, we've only focused our attention on longitudinal vibrations. Okay. However, these atoms can also oscillate in a transverse mode if allowed to do so. So there is going to be a vibrational mode which falls into the longitudinal realm, and two kinds of transverse oscillations, both of them perpendicular to the chain of atoms. So there are two transverse modes that are possible in addition to the one longitudinal mode that we've discussed so far. And each one of them is going to have its own dispersion relationship. All right, so if I were to relax this requirement of having only the longitudinal mode possible, then I could add two transverse modes to the scenario as well. So one possibility is longitudinal motion. Another possibility is that one of the atom goes up, the other atom goes down, up, down. This is a kind of a transverse oscillation. Another possibility is that one atom goes to the left, the other atom goes to the right. This is also transverse. So two kinds of transverse modes are possible, and each one of these oscillations will have a dispersion relationship of its own kind. So if I were to draw the dispersion relationship for these vibrational and acoustic modes at the same time, so I put K here and I put omega here, I'll get an acoustic branch corresponding to the longitudinal waves. Let's call this an LA branch, longitudinal acoustic. And I might also get transverse acoustic bands and two kinds of transverse acoustic bands, which means, and if the situation is symmetric, both of these bands can overlap with one another. So I have a doubly degenerate transverse acoustic scenario. I could also have a longitudinal optic band and two doubly degenerate transverse optic bands. So I can have quite an interesting and a rich scenario of acoustic and optical bands. And each one of these bands could be of the longitudinal kind or the transverse kind. And the dispersion relationships for the longitudinal and transverse don't generally overlap because the spring constants, the effective spring constants are going to be different inside these different kinds of oscillations. So suppose I have, now I also do know that inside my first Brillouin zone, so if I plot my first Brillouin zone between pi by A and minus pi by A, let's focus our attention on the longitudinal only. I have an acoustic longitudinal band and I have a longitudinal optical band. All right. Now, I also know that in each one of these bands, there are capital N K values, where capital N is the number of unit cells. So there are N K values inside the acoustic band and there are N K values inside the optical band. All in all, there are 2N K values inside the two bands. All right. So if I had, remember this is a divalent atom. If I had a monovalent atom, I would just get the acoustic branch, just N K values for the monovalent atom. And that's because only 1 degree of freedom is possible for the atom. It can only show longitudinal motion, and there's only one kind of atom. All right. So, and there are N atoms in overall, so there are N degrees of freedom. N atoms inside the solid, Sometimes I need to turn on the video. There are n atoms inside the solid. Each atom can only oscillate in a longitudinal fashion. So there are n degrees of freedom. So all the k values take into account all the degrees of freedom inside the system. If I have a divalent situation, the situation that I've shown over here, there are 2n kinds of atoms. Each atom has 1 degree of freedom. So there are 2n degrees of freedom inside the solid, and all of them are captured inside the first Brillouin zone, which therefore is necessary and sufficient to describe the oscillations of this material. Suppose I have a trivalent unit cell atom. Trivalent monovalent means, sorry, in this context, monovalent means one kind of mass, and diatomic means two kinds of masses. So it's not monovalent, it's monoatomic. I'm sorry about that. It's monoatomic. Suppose I have triatomic unit cells, tetraatomic unit cells. Then I'll have optical branches and I'll have acoustic branches, and I'm allowing the possibility of transverse modes as well. So in all of these cases, if I have Z different kinds of atoms inside the primitive unit cell, and I allow completely for transverse as well as longitudinal oscillations, and there are n atoms inside the solid, then my total degrees of freedom are going to be 3Zn, out of which I will have 3 acoustic modes, which involves 1 longitudinal acoustic and 2 transverse acoustic, 1 longitudinal acoustic and 2 transverse acoustic modes, and the remainder 3Zn. So this is 3Zn minus 3n optical modes, optical degrees of freedom. Since the Brillouin zone already contains n atoms, so I'm left with the following formula. I will have 3Z branches in the dispersion curve, 3 branches of the 3Z, 3 branches will be of the acoustic kind, and 3Z minus 3 will be of the optical kind. And these branches subsume all the possible degrees of freedom inside the system. So I have an example for you here. So if you look at the screen that is in front of you at the moment, now these are 3-dimensional solids: lead, sodium, silicon. So transverse modes are of course possible here. So if you look at the left curve, I have 1 longitudinal acoustic wave. And this dispersion relationship, by the way, is drawn in the lead crystal structure with along the direction 1, 1, 1. The primitive unit cell is just 1 atom in lead. Remember, we're talking about the primitive unit cells here. So there is 1 kind of longitudinal branch inside the dispersion relationship, and there will be 2 transverse branches which will be overlapping with one another, totally degenerate. Okay, this is the scenario in sodium along a particular direction. Now, if you change the direction inside the solid, you will observe that in a different direction, in the 1, 0, 0 direction, which is along a cell edge, 1, 1, 1 is along the body diagonal. in the 1, 0, 0 direction, the longitudinal and the transverse branches in the dispersion relationship, they curve downwards slightly. And inside sodium, the two transverse modes, T1 and T2, now their degeneracy is lifted and they appear with different frequencies. Okay. For silicon, there are two atoms inside the unit cell. So there will be 6 branches in total. So 3 times 2 is 6, out of which 3 are of the acoustic kind, 1 longitudinal, and 2 of them are overlapping with one another and they form the transverse acoustic branch, and the remainder 3 are optical branches. 1 longitudinal optical and 2 transverse optic branches that are overlapping with one another. And notice that in the k equals 0 limit, the longitudinal and the transverse optic branches, they are all degenerate, and all the acoustic branches are degenerate, and they start off at omega equals 0. For another crystal structure, which also has 2 atoms per unit cell, potassium bromide along the body diagonal, this is what the dispersion relationship looks like. And in this case, at k equals 0, the longitudinal and the transverse optic modes, they don't overlap as they do overlap in silicon. So all of this is complicated stuff, but at least we should be able to count the number of transverse and longitudinal optic and acoustic branches. And now I would like to move on to phonons, and I would like to connect phonons with all of this. But are there any questions for the time being? All right, so let's now move on to phonons. Okay. Now, the first idea that I would like to start off with is the fact that if I have a harmonic oscillator, suppose I have a classical oscillator, a mass attached to a spring. There's a spring constant K, and of course there is going to be a natural frequency, K over M and root, right? So this is a natural frequency of this oscillator. You can call it a natural mode. Now, if we were to make this a quantum harmonic oscillator, then the correspondence principle states that the energy of this oscillator is going to be quantized, and it's going to be given by h bar omega n plus half, where omega is the normal mode, the classical normal frequency. So the energy gets quantized. Okay. Now, in the dispersion relationships that we've seen for the acoustic and the transverse branches, so I'm just plotting half of it because I know that the dispersion relationship is symmetric about K. So this is an acoustic mode. Now, there are different values of omega that are possible corresponding to different values of K. So each K will give us an omega. So I can put a K subscript with this. Okay. Now, therefore, if our atoms are taken as quantum harmonic oscillators, the amplitude of each harmonic oscillator will carry a certain energy, and that energy is going to be quantized. And I could label that energy as h bar omega k, where k is a natural frequency, nk plus half. So I can put, instead of subscript, and I could put a subscript k. So I'm going to explain this in a minute, but I hope you'll be slightly patient for the time being. Now, what is, if I have multiple atoms inside my solid, which can now, of course, be three-dimensional, now in this solid, I would need to define what is a normal mode. So for a single harmonic oscillator, the normal mode is quite simple. But how do we talk about normal modes of a multi-body system, a multi-particle system that we have in front of us? All right, so a normal mode is a mode of all the atoms of the solid in which each atom is moving with the same frequency. So what we could do is we can take certain modes, certain frequencies, and if each atom is moving with the same frequency with some predetermined phase relationship of oscillation between all the atoms, then we can construct a normal mode of the system. So in a one-dimensional chain, we saw that at k equals 0, the two normal modes are what they are in front of your eyes. One normal mode is that both kinds of atoms, they are moving in phase with one another with the same amplitude, and the other normal mode is that they are moving anti-phase with one another but with the same amplitude. Now, if a system is excited in normal mode, all of the atoms are moving with the same oscillation frequency omega k, then this oscillation, this normal mode will be sustained, will keep on going forever if your potential is truly of the harmonic kind. There are no inharmonic effects, there are no third order or fourth order terms in the potential, which means that the potential energy is purely quadratic. So if that is the case, you excite a system in a normal mode, it will always remain in a normal mode. So the normal mode oscillation, which is represented by a quantum wave function, is an eigenstate of the Hamiltonian. It's just like a superposition of oscillations, relative amplitudes between different atoms, which becomes an eigenstate of the Hamiltonian of the system. And the Hamiltonian is taken to be quadratic in displacements between the two atoms. So if there are n modes, there will be n normal modes, there will be n frequencies, n kinds of frequencies, and each frequency is labeled by omega k. So the overall solid can now be represented by a collection of quantized harmonic oscillators. And the normal modes are given by omega k's. All right. And we can find out what these normal modes are. So for frequency omega k, there is some frequency omega k. So I put omega k here. There is going to be some corresponding value of k. All right. And the energy is going to be given by, for that mode, is going to be given by ek. So this is the energy per mode, per the kth mode. And if I were to find out the total energy of all the modes inside the solid, I'll just sum up over ek. So I'll get h bar omega k nk plus 1/2. Now, what does this have to do with phonons? A harmonic oscillator. Now we have to talk about a combined harmonic oscillator. So our overall system is a multi-body system. It's many harmonic oscillators combined together, and they're defined by their normal frequencies omega k. So each of these harmonic oscillators with a normal mode frequency omega k is can be defined as a collection of oscillations. So if I were to take a harmonic oscillator, so this is something that you've learned in quantum mechanics too. There's a potential energy curve which is quadratic, which means U is proportional to x square, where x is the deviation from equilibrium. Okay, and you found out that there are equally spaced energy levels. The lowest energy level is quite luckily not equal to 0. It's some h bar omega over 2. Omega is the normal mode frequency of this oscillator, and there's a spacing between these levels which is given by h bar omega. And if this harmonic oscillator represents, say, an electromagnetic field, then what you could do is you could go up this ladder by creating quantized units of energy, quantized units of the electromagnetic field, and you give those quantized units of the electromagnetic field a certain name, and that is a photon. But the electromagnetic field is not the only kind of field. You can have an oscillation field as well, and that's what we have in our scenario. In our scenario, we have an energy Ek, which is quantized in exactly the same fashion. So each quantum of vibration is called a phonon. So there are phonons of mode K, and you can have these phonons which are now being treated as particles in the ground state, which means that the energy of the system is going to be h bar omega k, because nk is 0. So the energy is h bar omega k over 2. Or you can have this system in an excited state, which really means that you are creating more and more phonons. So if you are in the nth excited state, you can imagine that you have n phonons in your system. Okay, so this is the concept of phonons. A phonon is a quantum of vibration, and it represents an oscillation mode of frequency omega k and wave number k, and you can excite more and more phonons into the system, which means that you are really incrementing the value of nk. So if I look at this from a conceptual perspective, if I go up this ladder, I am creating phonons, these quasi-particles, phonons. And if I go down this ladder, I am absorbing phonons. So going up the ladder really means that the atoms are oscillating with a fiercer amplitude, with a higher amplitude. I'm adding more phonons into the system. More phonons are being emitted into the system. And if I'm cooling down the system, for example, which means that the amplitude of oscillation is going down, I'm absorbing phonons. Those phonons are being annihilated. So this is the picture that emerges from the correspondence principle. The harmonic oscillators are now treated as quantum harmonic oscillators, and we have normal modes in which all of those atoms are oscillating with the same with the same frequency, with a particular phase relationship between the atoms. that represents a mode of oscillation, and those modes are quantized, and the quantization field is called the phonon field. And you can have a particular mode in the ground state or the excited state, which is tantamount to saying that phonons are created or they are absorbed. Higher energy means more phonons are present, and these phonons are bosons. So for each mode, you don't need to have just one phonon, you can have many phonons because these phonons are bosons, just like photons are bosons. That's why you can have many phonons in the same mode at one time. Okay, any questions? And I'll give more examples of this in a minute, but any questions about the concept of phonons? And this concept, by the way, of quantized oscillations is just one of the many concepts in condensed matter physics in which we talk about excitations of some field. The photon is the excitation of the electromagnetic field. The electron is an excitation of the electron field. The phonon is an excitation of an oscillation field, and so on. Okay. Likewise, we have excitons, we have magnons, we have polaritons. So all of these are excitations of some quantum field, and they can be visualized as being particles. These particles are generally called quasi-particles. And the nice thing about these particles is that they have a K, which means that they have some momentum and some energy. Okay. So they can be treated as quasi-particles. Phonons can also be treated as quasi-particles. They can be absorbed, they can be emitted, they can interact in a scattering experiment with other objects, with other photons, or with other neutrons, with X-rays, and so on. Okay. So any questions up till this point? Have you studied phonons in the statistical mechanics course?
So these are just quantized sound waves, just like photons are quantized light waves.
Sound waves is just one kind of an elastic wave. It's a really long wavelength wave, so it's not just sound. And really, one could say that these are the oscillations. Okay, if you want to define phonons, you'll have to make an argument for that. You would say that the system which comprises of atoms which can vibrate, they have normal modes. Each normal mode is a set of phonons. Okay, and the normal mode can be described by one phonon, which is a phonon in its ground state, or by excited phonons, which means you have many phonons in the system. So it's really tricky to say that it is a quantized wave. You're saying that quantized wave isn't making any physics sense to me in terms of physics. There's no such thing as a quantized wave. What does it mean? All right, so it's a quantum of oscillation. That's, I think, the best description that you can give it. But there are certain terms that cannot be described in one-liners. You need to build an argument for them, and phonons, I think, is one of those. Electrons are also fields, but we are accustomed to dealing with electrons as particles because this is how the concept of electrons developed. They were particles that carried a charge, they carried a momentum, they could exert pressure, they could be deflected inside magnetic fields, and so on. Okay, Daud?
Okay.
So a system at some temperature will have certain number of phonons inside the system. And since these are bosons, they obey Sorry, I just got disconnected. So have you studied Bose, Einstein, and Fermi-Dirac statistics in statistical mechanics?
Yes sir, we did it. और फोनों भी पढ़े थे तो हमने
किसमें पढ़े थे?
फोनों भी हमने पढ़े थे उसमें.
ठीक है.
फोनों को एज अ फ्री पार्टिकल हम डिस्कस किया था.
Very good. All right. So so these phonons, they are spin zero particles, and uh, they are bosons, and we know that the bosons have a certain occupation factor or an occupancy factor. So if we have a collection of these bosons, so let me just draw a cartoonic representation. So I have a bath of
He
bosons.
was not sure.
Excuse me, sorry. So now I have this bath of bosons, which means I have a solid which can oscillate, in which the atoms can oscillate, and we consider the normal modes. By the way, the real oscillation of the atoms inside a solid is going to be a superposition of normal modes. So if I have an atom which is frozen at 0 Kelvin approximately, and I just take one atom and oscillate, put it into motion, then of course this is not a normal mode, but it's going to be a superposition of normal modes. All right, and it will decay with time. A normal mode, however, will not decay with time if you have a purely harmonic potential. Anyway, if I have a bath, generally we talk about baths of phonons. If you have a bath of phonons at temperature capital T, then for a normal mode, some normal mode, there is going to be a certain average number of phonons, and that average number of photons that will have been emitted inside the system, that will be present in that system, is called the Bose occupancy factor, and is given by, suppose, the expectation value of the number of these bosons is given by this expression, which is called the Bose Einstein occupancy factor. So this, by the way, is the number of photons of the normal mode omega that are present inside the system at the temperature capital T, where Kb is the Boltzmann constant. All right. So if I were to talk about, so I could use the label, either I could use the label omega or I could use the label K. It doesn't really matter. So I can write this as H bar omega sub K as well. Omega sub K, of course, omega is a function of K, and this comes from the dispersion relationship. So this is the number of bosons, number of phonons that will be excited at a temperature T for a mode K, for the kth mode inside the system. Got it? So I'm going to repeat this. This is the average number of phonons excited or emitted or present inside the system of the mode, of the kth mode, which means a momentum K and an energy omega K. Okay, so this is my momentum, this is my energy at the temperature capital T. So of course the each if I talk about n number of particles, each particle has an energy h bar omega k. So one view of looking at this harmonic oscillator is that there are n. So let me come to this equation here. One way of looking at this equation is that this is the number of particles excited, number of bosons, and this is the energy of each one of them. Okay. So in this picture, if I were to find out the energy in the kth mode and the expectation value of that energy, that will be given by h bar omega k nk plus half. And if this is much larger than half, which means that the temperature is much larger than 0 kelvins, I can sometimes ignore this 1/2. Okay, and I can also insert the value of nk in here, this nk, this Bose occupancy factor, and I can arrive at a relationship for another alternative relationship for the energy. So the total energy of the system, which is the energy of the system at temperature capital T, and this is only the considering the energy not of the electrons but just of the oscillations of the atoms that make up this solid. I'll have to sum up over all these modes. And by the way, I'm summing up over all K's inside the first Brillouin zone. By the way, when I restrict the wave number k to the first Brillouin zone, then that momentum is called the crystal momentum. But we'll talk more about that later. So this is the total energy of the system in which you've summed up over all modes. So this sigma k is really a sum over modes. And for a one-dimensional solid, as well as for a two or a three-dimensional solid, we know that these k points are spaced really close together. In 1D, they're spaced 2 pi over L apart, where L is the total number of atoms inside the solid multiplied by the unit cell spacing. So this is my delta k. So I'm tempted to replace this sigma k sometimes with, if I were to make these calculations physically for real systems, I would be tempted to replace this sigma k with some kind of sum over k inside the first Brillouin zone. And how could I do that? By the way, what does the sum over k mean? This means that k is some 2 pi over L, some unit of 2 pi over L. But since I have to remain inside the first Brillouin zone, m has to be bounded on the lower side by n over 2 and on the upper side by n over 2 minus 1. So I have n modes. Total number of modes is still n inside the first Brillouin zone. So I'm tempted somehow to replace this sigma with an integral. All right. Now, any ideas how I could do that? So first of all, why am I tempted to make this sigma, this discrete sum, look like a integral? Because I would like to do calculations. Integrations are easier to do than mode counting. The second motivation for this is that the k values are really spaced close to one another. So the discrete sum tends to an integral in any way, in any case, unless you're dealing with nanomaterials with and just few atoms are at stake. So, but is there a quick way, a quick conceptual way in which I can replace this integral with the summation or vice versa? In 1D, if I'm summing over k, so in 1D, I have some k's. So this is my k axis. And I have pi over a here minus pi over a here. and the spacing between 2 points is a meager 2 pi over L. So if I were to sum up over the first Brillouin zone on this K line, I will simply do a counting in this fashion. I will count all the values of K, but each K has a length 2 pi over L. So this is the smallest volume on the K line of a single K point, it's 2 pi over L. So if I were to make, I can always make a substitution from a summation to an integral over K by pre-multiplying the integral with L over 2 pi. This is in 1D. In 3D, I can also make a similar substitution. In 3D, my volume of a point in the reciprocal space is now given by the total volume of the solid divided by 2 pi cube. So this was also the first question in homework number 6. Anyway, so I can always, if I were to find out the total energy, I could replace this summation with an integral t cube k, and then I have h bar omega k nk plus 1/2. And the energy per unit volume is given by 1 over 2 pi cube d cube k h bar omega k nk plus 1/2. All right. So, by the way, and from this energy, total energy, I can always find the heat capacity at constant volume, and so on. So one thing I would like to mention here is, and this is probably homework, some homework problems in homework number 8. So one concept that I would like to bring home at this point in time is the concept of the density of states here, as applied to these phonons. Remember that if I were to take a sum over k, so suppose I'm in 1D. If I were to take an integral over k, I can always express this as an integral over omegas. So my modes can be defined by k's, and my modes can be defined by k's, and they can be defined by omegas in an equally respectable fashion. So I can integrate over k, but in some cases I would like to integrate over omegas, over the frequencies, over the energies. And we know that the density of states is the number of states per unit energy. So energy in this case is like omega. So dk can be written as d omega with dk over d omega. All right. So what we could do is actually I could rewrite this as, sorry, excuse me. What I could do is, just give me a second. dk is, so if I were to sum over dk's, integrate over dk's, and I'm in 1 dimensions, I can, sorry, put the prefactor L over 2 pi. This is a mode counting, right? This is mode counting. In other words, this is the equivalent of sigma k. So this is the number of modes inside the system, and the number of modes inside the system between the edges of the first Brillouin zone is given by this. And I can equate this is my definition. I can equate this to an integral over the frequency space or the energy space with some metric or some measure g omega. So I can replace this dk with d omega, g omega, and have omega go from 0 to some omega at the boundary of the first Brillouin zone. But since I'm taking omegas to be positive, the energies are taken to be positive, I multiply this with 2. Okay, because the k, a positive and a negative k, will give me the same value of omega because of the even symmetry of the dispersion relationship. Okay, so but this dk is also equal to dk d omega over dk, g omega. So I can break up this d omega into dk, d omega over dk. All right. So, but d omega over dk is also called the group velocity. Okay. So my so now if I compare this expression with what I have over here, I can immediately say that my g omega is L over 2 pi divided by d omega over dk. Okay, so my g omega is can be found out from this relationship. Now d omega over dk is found out from the dispersion relationship. And this is what my density of states is going to look like. So suppose I have a monoatomic lattice, a monoatomic crystal. I know that my omega, the relationship between omega and k, is given by sine ka over 2, right? This is, if I remember, 2 alpha over m sine ka over 2. Right? We derived this dispersion relationship. Now I would like to find out the density of states for these acoustic phonons. So I have an acoustic branch, and I'm saying that that this part of the dispersion relationship accounts for acoustic phonons. Now I have the dispersion relationship in front of me. This is my zone boundary, pi over a and minus pi over a. What I could do is I could find out the group velocity d omega over dk 2 alpha over m cosine ka over 2 a over 2, and then put this into the expression that I've derived over here. I will get g omega. G omega is going to be given by L over 2 pi 2 alpha over m a over 2 cosine ka over 2. So the density of states is going to look like a secant function, probably of this kind. When k is 0, this is 1. The density of states is not constant. There are more modes. In other words, there are more modes with a value of k closer to the zone boundaries. All right. And in order to find out the energies, what we would need to do is we would need to look at the energy of the omega mode, which is h bar omega, multiply this with the density of modes, and multiply this with the occupancy factor and sum over all omegas. This will give me the total energy of the system. Okay, so we have the energy, we have the density of modes, how many modes exist per unit energy, per unit omega, and what is the likelihood of their occupancy. This is like a probability metric. Okay? This is the probability metric. So this is how we can compute energies of a phononic system. And then once we have the energies of the phononic system, we can always find out heat capacities and other kinds of thermal properties. By the way, one do-it-yourself problem would be if I would take n omega, which is given by E h bar omega over kBt plus 1. And if I'm at high temperature limit, which means kBt is much larger than h bar omega, then this would become, now kBt is large, which means that this exponent is small. So I can replace this exponent by this thing. By the way, there's a minus sign here. Sorry, this is minus. 1 plus h bar omega kBt minus 1. So this 1 goes away, and I'm left with n omega in the high temperature limit is given by kBt over h bar omega. Okay. So this means that my total energy can be given by, is going to be proportional to d omega, n omega, which is kBt over h bar omega, the energy h bar omega, and the density of states. The density of states is g omega is given here. All right. So this will give me the total energy of the system. And it's proportional to, by the way, temperature. So at high temperature, if you were to find out the heat capacity, it's going to be some constant. And you'll find out that this is equal to 3 times the number of modes, number of atoms inside the system. This is called the Dulong-Petit law. So I'll have some homework problems for you in this respect. So I would like to finish the lecture now. Any questions? I'm preparing homework number 8 so that you can get some felicity on problems of this kind. Any questions, my friends?
नो सर क्वेश्चन नहीं है सर, लेकिन जो आज वाला लेक्चर है इसके लिए आपको रेलेवेंट रीडिंग अपलोड कर देंगे साथ, क्योंकि इसमें इक्वेशन मैनिपुलेशन काफ़ी थी, तो इट वुड बी गुड कि हम कहीं से इसको रीड करके स्टेप बाय स्टेप सारा देख लें.
I'll find out something, because this is not from a particular source. It's just I won't say my random thoughts, but I've prepared this lecture formally, but I'll see if I can find a relevant resource on this material.
All right, sir. Thank you.
All right. So thank you very much. Inshallah, see you on Tuesday. Khuda Hafiz.